thank you very much for the invitation. It's very nice to be here. And what I would like to speak about today are random processes on infinite trees, mainly on the infinite deregular tree, and the connection of these processes to random deregular graphs and the methods of entropy that we could use to prove results about the structure of random deregular graphs, let's say. So for motivation, we just have the infinite deregular tree, and since this is a very boring structure in the sense that it's like deterministic and very, very symmetric, we add some randomness. More precisely, we assign random variables to the vertices of the tree, and if the joint distribution of this family of random variables is invariant under all automorphisms of the tree, then we will call this an invariant process. And the question, our main questions in this work, which was, sorry, I will go back to the beginning. So this is joint work with Sharp, Bordenave, and Balázs Szegedi, and Balázs is here in the audience. So the main questions were what kind of entropy notions can we use or define, and how can we use entropy inequalities to obtain new results about the structure of random deregular graphs. So random regular graphs, these are quite simple combinatorial objects, so we fix the number of vertices and the degree, so all vertices we have degree d, and given these two numbers such that n times d is even, we consider all simple graphs on n vertices with this very simple degree structure, and we choose just one of them uniformly at random. And graph limit, so our approach also comes from graph limit theory, so there are close connections to the structural properties that are interesting from the graph limit theory point of view as well, And so to start, what is the connection between such a finite object and the infinite deregular tree that I showed you and promised that we will assign random variables to the vertices? So the local limit of random deregular graphs is the infinite deregular tree if you keep d fixed and tend to infinity by n, which is the number of vertices. What do I mean by local property, local limit? If you just sample a vertex uniformly at random from the finite graph and look around in its neighborhood, then with probability tending to 1, it will look like a tree, because random deregular graphs does not contain many short cycles. But this is so this is the starting point. So random deregular graphs tend to this deterministic object. But the really interesting question here for us was that how can we characterize the invariant families of random variables on the infinite deregular tree, which can be approximated with labelings on random deregular graphs. So first we choose a random deregular graph, then we can write some labels or numbers on the vertices. We can take a limit in some sense. I will define that more precisely. And in the limit we get this kind of random process on the infinite deregular tree. And the question is, which invariant processes can arise in this sense? So this was the introduction, and I will for the talk I will first show an example which will be very important later on, Then I will speak about the entropy notions that we used. I will define typical processes, these processes that we can model on finite irregular graphs. And then about necessary conditions and sufficient conditions for a process to be typical. And finally, applications for branching Markov chains, if I have the time, and some extensions. An easy example for an invariant random process on the infinite irregular tree is a branching Markov chain. When a root flips a fair coin, we consider this as a message, and the message is passed along the edges of the tree, but on each edge it changes with probability p. And this is a very simple invariant process. Okay, my question was whether this process can be approximated on finite irregular graphs or not. So after randomizing a finite irregular graph, a large one, can you color the vertices such that the local statistics are similar to this one? And of course, it depends on p. If p is 1, you change the color for sure, then you get the alternating coloring, and it follows from a result of Bolobash on independent sets of random irregular graphs that this cannot be approximated with the colorings of random graphs. For p equal to 1/2, it's of course very easy because all colors become independent in that case. So a special case of our general question is for which we can we approximate this process on random irregular graphs. Okay, what do I mean by approximating? So we have the infinite irregular tree. We have a finite set of colors which we can write on the vertices. We have an invariant process, a family of S-valued random variables whose distribution is invariant under all automorphisms of the tree. And what we are interested in, that given R, what is the distribution of a colored neighborhood, of a colored R neighborhood of a vertex? And of course, it doesn't matter which vertex do we look at due to invariance. So on a finite graph, we will be interested in the colored neighborhood of a randomly chosen vertex among finitely many colors, and here we can look at any vertices, and we will compare the two, and that will be the limit notion. But of course this idea about looking at the distribution of these colored neighborhoods immediately leads to an entropy notion. Okay, this is not, so the definition is not the entropy of the whole process, but given the process and given a finite subset of the vertices, we can calculate the entropy of the joint distribution of the random variables assigned to the vertices in that finite subset, just simply the Shannon entropy. So this way, given a process and the finite subset of the vertices, we can measure entropy. This will be very important both for the sufficient and necessary conditions that I would like to present for a process to be approximated on finite irregular graphs. So what does it mean that an invariant process can be approximated on finite graphs? As I said, if we have a finite graph, we can just choose a vertex uniformly at random and look around in its two neighborhood, and the probability that the two neighborhood of a randomly chosen vertex is isomorphic to a given f. Sorry, I didn't define f. So f is just something which is on the figure. The probability that we see something which is isomorphic to this, so that the root is fixed. This probability should be convergent, and then we say that the sequence of colored graphs converges to an invariant process. So more precisely, and now this is like a precise definition. So we have a finite sequence of deregular graphs. We consider the set of connected rooted vertex colored graphs with diameter at most 2r, that is in this set F. And if for all R, radius R, and for all F, the probability that the colored neighborhood of a uniformly randomly chosen vertex of agent is isomorphic to F, keeping the root where it is. So this, if this converges to the distribution that we see in the invariant process on the infinite deregular tree, then we say that this sequence of finite graphs converges to that invariant process on the tree. Okay, and yeah, so if without colors, the graphs, random deregular graphs, converges to the infinite deregular tree. So the interesting question is, where do they converge, or where can they converge if we have more colors? And those processes are the processes that we call typical processes. So an invariant random process is typical if there exists a subsequence of the positive integers such that if we choose random deregular graphs on nk vertices with d fixed, then after we have the graph, so if we choose this independent sequence of random deregular graphs, then with probability 1, we can find those colorings fk from the vertex set of G to S, such that these colored graphs converges to the invariant process. So first we randomize the graph, and then we can color the vertices. And as I have mentioned from the result of Bolobash, it follows that that, for example, the alternating coloring is not a typical process, or if you just color the root uniformly at random to black or blue, and all vertices got the same color, that process is also not a typical process. So we will see that this is not typical. So the question, how can we prove in general such a fact? And before showing that to you, I would also like to just quickly make a small detour to Sophic entropy. So this notion of typical processes can also be defined by Sophic entropy. So, and sorry, I am very sorry. Here is the reference. So it's Bohan from 2012. So here we are given a probability measure mu, like the distribution of an invariant process, and we count how many ways can we color the vertices such that this local statistics are close to the given distribution. Then we take the logarithm normalized by n, and the process is typical if and only if. Okay, this is like a long definition. This is not very important for us. I mean, maybe the original definition was easier to understand. But I would like to emphasize here is just the connection. So the starting point of the definition of Stophic entropy is this quantity h(gn). So the normalized logarithm of how many ways can you color the vertices such that the local distribution is close to the given local distribution. And the main point in the very long formula is just that the same h(gn) is in there. So what do we have so far? We would like to say as much about these typical processes as much we can. So necessary conditions and typical conditions, and now it's based on entropy. There are other tools that can be used to give necessary conditions for similar processes, like in more special cases. But now we focus on entropy, and one can prove, and it was so it's a longer story that okay, we can define entropy for all subsets of all finite subsets of the vertex set of the infinite irregular tree once we have this invariant process. But if the process is typical, then we can find inequalities between the entropies corresponding to different subsets. Namely, if D is at least 3, then D over 2 times the entropy of an edge is at least D minus 1 times the entropy of just a point, so just the entropy of a single marginal of the process that we are interested in. Or the entropy of the one neighborhood of a vertex, including the vertex itself, is at least D over 2 times the entropy of an edge. And for example, this can be used to show that the processes that I mentioned that are not typical, if you calculate the entropies, then this somehow follows. So how can we prove such a fact? In the first step, I think there is so we cheat a bit in the first step because when I defined random irregular graphs, I said that uniformly chosen simple irregular graph, and now we use the configuration model. So we add half edges to each of the vertices and connect them according to a randomly chosen matching. But okay. And then, similarly to the idea that I mentioned in Stophic entropy, when we just counted colorings whose local statistics are close to a given distribution, we count the number of colorings that are close to the distribution of the process. And since the process is typical, the appropriate number of colorings has to be at least as large as the number of graphs, because typicality demands that I can color every graph so that the coloring is close to the given measure. So the number of colored graphs is appropriate colored graphs is at least the number of graphs, because almost all graphs have coloring. So I just quickly mentioned this other direction about correlation decay. But in this joint work with Sharp, Bordenave, and Balázs Szegedi, we were interested in sufficient conditions for typicality. I don't know about any necessary and sufficient condition. That would be very, very interesting, but now we just have necessary and sufficient conditions separately. And also similarly to the notion of Sophic entropy, one of the main ideas is just to consider larger balls as subsets that we calculate the entropy of. So of course, we cannot really hope that we could understand the behavior of large random regular graphs or invariant processes that can be approximated with large random regular graphs if we only focus on a single edge or just a small star. So of course, we need larger neighborhoods, and fortunately, and it's not hard to see, that similar entropy inequalities are also hold and also give sufficient conditions. If you increase the radius of the ball, you can just encode so you can just encode the colors of the vertices in a larger neighborhood to one single vertex with a much larger vertex set. With a much larger color set. Yeah, so if a color can be that I have, I don't know, 3 red and 2 blue neighbors, and I am colored to yellow, then you can just do this encoding, and then we have in some sense stronger sufficient conditions, because for arbitrary r, this quantity, which will be important for our calculations as well, this also has to be non-negative for typical processes. And the other main ingredient was a coupling. So instead of just looking at our invariant process, we take 2 copies of it. So from now on, it will happen that we write that we assign 2 random variables to the vertices, such that the coupling is also invariant. So in this case, the definition is that the joint distribution of x and x prime also has to be invariant under all automorphisms of the group, and we will so we couple an invariant measure whose both marginals are equal to mu. Mu was just the distribution of the invariant process that we were interested in, and we can have two very simple observations. First, if we couple just 2 copies of the same process independently, then of course all entropies will just double. So the difference that we are interested in, and what we know that is non-negative for typical processes, that will also multiply by 2. And the other extreme is the trivial coupling when just x prime is equal to x, and of course that has the same entropy. Okay, this is trivial, but now we know that the trivial coupling has at most as large entropy as the independent coupling, if and only if the difference is at least 0. And that was very interesting for us, because for typical processes that difference was non-negative. So maybe now it's not very surprising, but of course we have to do some work to to prove that, that we state that if for larger and larger neighborhoods, for all invariant couplings of the distribution with itself, we have that difference is at most twice the same difference for the original distribution, which would be the entropy or the quantity corresponding to the independent coupling. So if this equality holds for larger and larger neighborhoods and for all invariant couplings, then we can say that our process is typical. That is, if we have a family of random variables whose joint distribution is this mu, then that family of random variables can be approximated with labelings or colorings of random deregular graphs. So about this sequence Rk, this is not. Yeah, so we just need that there exists some appropriate sequence of Rk, which tends to infinity, and then for each Rk we have this condition about all invariant couplings. This is our sufficient condition. So what about this special case that I mentioned, the branching Markov processes? So here the question was, so P was the probability of the event that a message is changed on an edge. And the question is whether we can approximate this process on random deregular graphs or not. And it follows from not from this particular sufficient condition, but it's not very hard to see from conditions on correlation decay that if P is if the absolute value of 2p minus 1 is larger than 1 over square root of d minus 1, then the answer is no. If this quantity is smaller than 1 over d minus 1, then the answer is yes. Moreover, the process is a factor of the process for those who have met that. And there is a, yeah, sorry, I forgot to look up whether this was already published somewhere. I guess it was. I just forgot to look that up. So it is also known that we can go a bit above 1 over d minus 1. The authors don't give any particular values, but they can go a bit above 1 over d minus 1. Yeah, and our results do not improve those bounds in any case, but it's good to so even despite that we cannot improve those results, it's interesting to look at this particular case, because there we can have stronger statements, and these processes have also play a very important role in the proofs. So we say that the probability measure is edge Markov if conditioned on the values at the endpoints of an edge. The process, so the values, the random variables assigned to the vertices to the left of this edge and to the right of this edge are independent of each other. So this is a bit more general than the branching Markov process, but the branching Markov, still it has a special Markov property. So if we have an edge Markov process, then we can calculate this difference of entropies corresponding to the R, to the ball of radius R of a vertex, and to the ball of radius R-1 of an edge. And here we say that that if for every coupling Q of P and P, where P is a probability measure satisfying the conditions above here, so we have a probability measure which is invariant under the automorphisms of just the star, and invariant under switching the endpoints when we restrict it to an edge. So if a probability measure satisfies this condition, then the unique edge Markov process whose margin are restricted to B1 star has distribution P is typical. So the main point here is that for edge Markov processes, we don't have to check the conditions for larger and larger balls, but we have to. But it's enough to check the condition in just one neighborhood of a single vertex. We can. So the first idea is that we can extend this distribution of from the one neighborhood to the whole tree, and then if we check the condition for this small neighborhood, then the process will be typical. This can be generalized to larger neighborhoods as well, and these edge Markov processes were also important for us because they have an extremal property. So one can show that the difference decreases if you increase R. This is also from an idea which appears in the theories about Sophic entropy. But this decrease of the difference does not happen if this is an edge Markov process. Then we just have equality. So this is an extremal property of the processes, and we could use that in the proofs. And we could also obtain a sufficient condition for vertex Markov processes. So about the methods of the proof of this sufficient condition for typicality. So this is the first one, that edge Markov processes have an extremal property. This difference is the same if you increase R. And the other main ingredient is a second moment method for this quantity that was already mentioned. So here we have a probability measure on the colored R neighborhoods, and we want to count the number of labeling, or number of vertex colorings of a graph whose local statistics are close to this given measure, and we have seen that this was related to I had this long formula, so we could define typicality by using this as well, and a second moment method was applied to this quantity. We had to we had to show that this quantity concentrates. But our so far, for like sake of simplicity, I was speaking about random irregular graphs. But if you look at the paper, then you can also find you can also find that that these methods, these work for the case when the underlying tree is random itself. So instead of the infinite irregular tree, we can have a look at the Galton-Watson tree, and the same things happen there. Yeah. So this is just the connections to
Can I ask, so when you say for when the underlying tree is random, so how about for like possibly directed, maybe non-unimodular random trees? Is that?
So the question is what happens if the graph is if the edges are directed, right?
Or yeah, well, yeah, I'm wondering, yeah, what kind of random trees you're considering. But mostly Galton-Watson?
Only just Galton-Watson trees, where we can do this counting argument and second moment method. And so just some open questions that might be interesting. So is there sufficient condition about this entropy of the coupled version of the process itself? So is it also necessary, at least for special cases, at least for like edge Markov processes? That would be nice, because we don't really know any sufficient and necessary conditions for any particular cases. So even in the branching Markov process with two states, I showed you these cases with the 1 over square root of d minus 1 and d minus 1. So in the Ising model on the tree, we don't know what happens. So even in special cases, that would be very interesting. Also in general, and one more interesting open question, maybe. Sorry, but I will go back to the definition of a typical process. That's also an open question for, like, I don't know, more than 10 years from now. So when I defined typical processes, the definition started with if there exists a subsequence of the positive integers n, k, such that we can color the vertices of a random irregular graph. So a very natural question is, why do we need a subsequence of the positive integers? And the answer is that it's not known whether this definition is equivalent to the version without choosing a subsequence, just saying that for all integers we can color the vertices appropriately. This is equivalent to, the equivalence of these two definitions is equivalent to the question whether random irregular graphs converge in the so-called local global sense, which I don't want to define here, of course. Just mention that this question is about can be formulated in a graph limit language, asking whether these random graphs converge or not. And this question is, of course, about is it true that a random irregular graph on like 1 million vertices and on 1 million plus 1 vertices, so are those close to each other or not? And of course, locally, yes, because locally both look like a tree, but in general, it seems that we don't really know. And just a final remark is that I think I haven't written it there, but for this, yeah, sorry. So in the case when we had this edge Markov process and when we only needed to check the one neighborhood of the vertex, then it's not written there, but then from this condition it also follows that you can forget about this subsequential thing, and then this condition implies that you can color the vertices of a random irregular graph of any size if that is large enough. Yeah, and here are some references, and thank you for your attention.
Thank you very much. Other questions?
A bit confused by definition of typical process. If you could scroll back to the definition, when the first example is not an example.
So why is it not typical?
You can define a effectively constant one probability 1 half everywhere and a constant 0.
Yep, but you don't. So you can choose. Yeah. So it's not the. So once we have the. So we have randomized the finite graph. We have randomized the coloring of the process, and with large probability, those have to be close to each other in a local sense. And when I color the vertices of the random graph, I cannot have information what happened in the limit. I just color it as I can, and since so in that example, with probability 1/2 of the random irregular graphs, all vertices will be back, and the same holds on in the limit. But those are not connected. So when I color the vertices of the finite graph for black, then I cannot be sure that it's like the same event that happened.
It has to be known by local rule, right?
Yeah. So it's yeah.
So for this one parameter family of this telephone process, is it known that the parameters for which it's typical form an interval?
I don't think so. So in this case, in fact, I don't know about any particular conditions about this question for typical processes. All that I know is about factor of IID processes, which is a subset of typical processes. Okay, then I contradict to myself because yeah. Okay, no, sorry. I draw that back, but I don't think I would know any result stating that there is a critical P under which this is typical and above which this is not typical. We just don't know.
I guess it's closed set of P for which it's typical.
Yeah, but we don't really know.
So I mean, do I understand correctly that the proof goes by reducing to these edge markup processes?
Yes.
I see. So in fact, it's enough to check the conjecture for this kind of processes if you want to show the convergence of random regular graphs. Is that
yeah, that's a good question, but I don't know it right now whether it follows.
So basically, when it's an edge markup process, and there is a way to do it, sort of construct these things by hand on a finite irregular graph, right?
Yes. Yes. Yeah. So. Yeah, but I don't know whether I don't know whether this conjecture about the convergence of random graphs would be sufficient to check for edge markup processes. I don't know that.
I just want, what's the intuitive meaning, of this inequality, this entropy? Is it something it's a computation, or is there an intuition behind this? For typicality, why is it somehow?
So, where was it? Sorry, I had something. Yeah. So here the proof goes by a double counting argument in some sense. So we start and that gives some kind of intuition. So for example, in the configuration model, from each vertex we start some half edges, and if we are given the distribution of these colored van neighborhoods, then before constructing the graph, I can color these vertices with their van neighborhoods, and I can try to match the half edges after that, so that only half edges with the same with endpoints of the same color are matched to each other. So I can somehow do in a parallel way the construction of the random irregular graph and the coloring. And there I can do a double counting argument, and typicality means what this last line somehow would like to suggest, that if I can color every graphs appropriately, or almost every graphs, then the number of ways how I can match in the configuration model these colored half edges has to be at least the number of graphs. So that's the intuition behind this, and we have some counting there. And from this point of view, entropy is just like a short way of writing how many appropriate colorings do we have.
Question. Thank you very much.
Thank you for